Hello and welcome to the sixth session of NPTEL. So, I am Umar Rashid and I am currently working as a PhD student in Indian Institute of Science, Bangalore. I'll be helping you with solving some of the assignment questions that has been given in the past year, and with that, I'll be briefly discussing about some of the fundamentals that are needed for the solution of the in order to solve those questions. Okay, so in the past session, like session 5, we have discussed some of the questions. Okay, so that okay, yeah, so in the 5 we have discussed up to question number, yeah, we have discussed up to question number third. So today we'll be solving question number 4. These questions are related to the chemical kinetics and chemical kinetics and the rates of the reactions. The chemical kinetics is the branch of science or the branch of chemistry which is dealing with study of the rates of the reaction. Okay, so as if you can see in the previous session that is uploaded on the NPTEL, that we have solved some of the questions, and which we have also derived the equations for integrated Layla for first zero and second order reactions and even the third order reactions, and consequently we have derived and we came to the conclusion that different reaction mechanisms will have a different rate of the rate constant. So from the rate constant you can determine exactly what is the order of a reaction. We have also briefly discussed about an what is the order of a reaction, and for orders can be even negative, or the order of a reaction can be even fractional, and the order of the reaction is determined experimentally, and for multiple step reactions, that means where a reaction is not going in a single step. Yeah, so let me briefly discuss about this is the session 6. Okay, so as I have discussed in the previous lecture, what is an order of the reaction, right? So order of the reaction is actually the stoichiometric coefficient. If we say that we have a reaction, okay, our reaction is just a second, yeah, so if we say that we have a reaction A plus B, that gives us C plus D. Okay, so and from the experimental method, we determine that rate of the reaction actually depends upon A raised to the power 1 and then B raised to the power 2. Okay, so what we can say that the total order of a reaction is total order of the reaction is 3, but the order of a reaction with respect to A is 1 and the order of a reaction with respect to B is 2. Okay, so depending upon for example, so if we see that this reaction, even though the stoichiometry appears 1:1, but the mechanism of the reaction, if we follow, that it will be such that there are multiple steps that are involved in the reaction, and in a particular rate determining step, what we have is we have a reaction that is an elementary reaction or a one-step reaction where two moles or two molecules of the B are actually colliding in order to form a product. Okay, so that is briefly the order of a reaction. Similarly, as I told you, the order of a reaction can be negative, it can be positive, or it can be fractional. Okay, okay, so if the order of a reaction is negative, that means if order of reaction is negative, okay, so if the order of a reaction is negative, then what will happen is that the rate of the reaction will decrease. with increase in concentration. Okay, so that actually what is the physical significance of the negative of the reaction. For example, if I will show a reaction here, A plus B gives C plus D. Now if I say that the rate of the reaction is rate constant, okay, it depends on A raised to the power 1 but B raised to the power minus 1. Okay, if we increase concentration of A, then rate of reaction will decrease, sorry, rate of reaction will increase. Okay, Rn. But if we increase concentration of B, then what will happen is rate of reaction will decrease. Okay, so that is the order of a reaction. So this complex order, if you see, we have a multiple reactions in which we can see very complex, or like 3 by 2, 4 by 2 and everything. Those reactions are not elementary reactions, they are multi-step reactions. Okay, for elementary or you say like elementary or a single step reaction, you will always have order that's in that's a positive number. Okay, but for multi-step reactions, sorry, for multi-step reactions the order can be anything like negative, fractional. Okay, so that is a possibility. Okay, so let us go back to our questionnaire and we'll see what is the question we have. Okay, now here question number 4 we are trying to solve. For a zero order reaction between X and Y, the amount of X reacted was 80% after 2 hours. How long will it take to make the concentration of X to be 10% of initial concentration? Okay, so what we have been given, that a particular reaction is X plus Y gives something. Okay, the amount of the X that was is 80% given after 2 hours. So we have to take how much when will be the time when the concentration will be only 10%, that means 90% has been reacted. Okay, so how we'll solve that? We'll use the simple rate law equations. Okay, so I will write here solution 4. Okay, so what we'll do is we'll see that let the initial concentration of X, so we'll take the initial concentration of X as X naught. Okay, now what we have is how much will be the amount of X reacted after 2 hours. Okay, so it has been written 80% of X naught. Okay, so we can determine that 80 divided by 100 multiplied by X naught. Okay, that means 0.8 X naught. So this much amount has been reacted after 2 hours. Okay, now what will be the amount that is of the X which is unreacted? Okay, so that will be obviously 1 minus 0.1 X naught. Okay, so that will give us 0.2 X naught. Okay, now we know that for a zero order reaction we'll go to the integrated rate law methods. Okay, for a zero order reaction, X, that means the amount that is present at any point will be the x naught, the amount that was taken initially, minus kt. So this will tell us amount of x that remained unreacted, okay, at time t. Okay, so unreacted, we know that we'll put the value of this, so we'll write 0.2 multiplied by x naught, because this is the amount that is unreacted, will be equivalent to x naught minus kt. Okay, now we'll do some rearrangements. 2k will become equivalent to x naught minus 0.2 multiplied by x naught, that is 4 by 5 x naught. Okay, then k will be equivalent to 2 by 5 x naught mole per liter per second. Okay, so we determined the rate constant. Once we determine the rate constant, we can determine how much amount is unreacted. So how we determine the rate constant is from the zero order reaction. So I'll just briefly tell you how to okay, so briefly I'll tell you how to, for a zero order reaction, how we can proceed. Okay, so for a zero order reaction, we know that a rate of a reaction for a zero order reaction, that is given by, since here we are concerned with x, d of x by dt will be equivalent to k of x non as a function of 0. That means d of x by dt will be equivalent to k. Okay, now dx will be equivalent to k dt. Now we'll I'll write here, this is for a zero order reaction. Okay, okay, now integrate from t is equal to 0 to t is equivalent to t. When t was 0, our x was equivalent to x naught, and at t x is equivalent to x. Okay, so once we integrate that, we will determine, if we integrate, this will be x is equivalent to k t. So our upper limit is this. Okay, so we have derived this equation. Okay, x is equivalent to x0 minus kt. So we have to write upper minus lower. Okay, x0 minus x is equivalent to minus k, that will be become 0 minus kt. Okay, then x will become equivalent to this and this, it will be minus x will be equivalent to minus this, and so here it will be 0. Okay, since we are determining the rate with respect to the reactant. So here this dx divided by dt, this will be negative. Okay, so once that will be negative, what we can do is this will be negative. Okay, this will be whole negative, so we can do, okay, so that means x minus x naught is equivalent to minus kt. Okay, so this is plus, okay, this, and x0 will be minus. Okay, then we'll write x will be given by x naught minus kt. Okay, so we have determined the rate law for a zero order reaction. Okay, now we have used this. Now from this equation, what we have got is, we have got what is the value of the k, that means the rate constant of the equation. Okay, now from that equation, now since we know this equation we know, okay, we can determine anytime. Now our question tells us that when will be x in 10% unreacted. So when will be 10%, when x is 10% unreacted, that means how much will be amount of x left, that will be 10 by 100 multiplied by initial reactant. Okay, so what we can do is, we will use that equation. This is zero point 0.1 x plus x naught, no, is equivalent to minus kt. Okay, now we have to put the value and rearrange it. What we can write is 2 by 5 x naught multiplied by t, this value is equivalent to x naught minus 0 0.1 x naught, that will be given by 9 by 10 x naught. Okay, so skip by 9 by 10 x naught. Okay, so what we can do is, this and this will go cancel. Okay, and from that value, what we can determine is, we have t now, so t will be equivalent to, what will be t equivalent to 9 by 4. Okay, that is equivalent to 2.25 hours. So that solves our question. So what we have done is, we have first determined the rate constant of the zeroth order equation by using the rate law. Once we know the rate constant of the zero order reaction, then we can use the integrated rate law for the zero order reaction to determine the time or the amount that is unreacted or that has been reacted at any point of time. Okay, so that solves our question number 4. Okay, now we will go to question 5. Okay, so what is the question 5? It should be on this side. Okay, in a pump probe experiment, Okay, now we have question number 5. Okay, so in a pump probe experiment of sodium iodide by Ahmad Zavel and co-workers, the detected emission and the oscillation in the emission were due to. Okay, so this is regarding the uh, uh, pump probe experiment. Okay, we have to determine the emission and the oscillations. Okay, so emission and the oscillations which are happening due to the emission. Now we have to see when in a particular compound an emission can happen. Okay, an emission will happen in a particular compound when an electron will go from a higher orbital to that of the lower orbital. Okay, so go a little bit about so see in a so the fundamentals of the absorbance is, so what we do is we give an HA. So we have a state A or any molecule or any compound, and what we do is we give H nu. Okay, so once we give H nu, it changes to A star. What actually happens is, for example, I will take a simple atom. Okay, so consider this is a nucleus and these are it is orbitals. Okay, then what will happen is an electron that was initially present here, for example. Okay, once the energy has came, like this is our, so what will happen is this will get excited to this state. Okay, H nu. Okay, the delta E between these two H nu will be the difference between this. So this process is called as this is absorption. Okay, absorption. Now an absorption will not happen in a particular molecule or any particular system when you don't give a light that is equivalent that of delta T. Okay, so this is just the Bohr's principle. But when you have a system where, for example, I will make another atom here. Okay, for example, this is another atom. Now the electron is actually present at the higher orbital. Okay, so what will happen is that this electron can come to the down orbital. Okay, de-excitation can happen. That will lead to the emission of an energy. Okay, and this process is called as an emission. The energy that is given is also equivalent to delta T. Okay, we have an emission and we have an absorption. Now when absorption happens in atoms, the electrons or a molecule, the electrons can go from different between electronic states. Okay, that's what an atom has, electronic states. Okay, or okay, now when it goes in between a molecule will have a for a particular molecule. Okay, okay, so in a molecule there are different degrees of freedom. Okay, the degrees of freedom are okay, the first degrees of freedom they came are called as translational. Okay, then vibrational, then rotational. Okay, the total degrees of the freedom for a particular system is equivalent to n multiplied by number of atoms. Okay, where n is equivalent to number of atoms, yeah, entities. Okay, these are the total degrees of the freedom. For example, if we have H2 molecule, okay, the total degrees of freedom are 3 multiplied by 2, that is 6. Okay, out of these six molecules, 3 are translational. Okay, one is vibrational and another 3 4, then we have 2 are rotational. Okay, similarly, because we have H here, okay, then this and this. Okay, okay, this is H, this is another H. Now if we have a second compound, now if we have a second, for example, carbon dioxide. Okay, so it's a linear compound. Okay, so for a linear compound, you will have, obviously the total degrees of freedom will be 3m, that will be 9. Okay, degrees of freedom. Out of these 9 degrees of the freedom, uh, 3 will be translational, then vibrational will be 3 and minus 5. Okay, so this is 6, 9 minus 5. Okay, sorry, it should be 9. So it will be I think 9 minus 5 or 9 minus 6, I don't remember right now properly. Okay, and the rest will be rotational. Okay, but for some system like which is a bent molecule, for example water, similarly we have 3 n degrees of the freedom, there will be 9 degrees of freedom in total. Okay, here you have 3 translational, 3 translational. Okay, then you will have, I think 3 n minus 6 is here, so you will have 3 vibrational, then this is 6 is 3 rotational, so here will be 4 vibrational. Okay, you know in carbon dioxide what are the 4 vibrational. Now when we give a molecule or a when we have a molecular system, okay, and we give, okay, so when we have a molecule, okay, so for example in case of a carbon dioxide, okay, I'll take an example of carbon dioxide. I'll just show an example. We have this carbon dioxide molecule. Okay, the first, obviously there will be 3 uh, translational degrees of freedom. Okay, translational degrees of freedom has been represented by the green color. Okay, so what in translational degrees of the freedom, what will happen is that the translational motion will happen. Okay, that translational motion where the center of mass changes, it is position. Okay, this is translational. Now the second thing that we can have is the rotational. Okay, so this is carbon dioxide. Okay, now you will have rotational through different axes. Okay, so particularly here you will have 3 rotational axes, so I will determine by blue. So this is one rotational axis. Okay, for example I will call it rx, then we have another along this is ry. Okay, along this, and then third we have is just an opposite this thing, this is rz. So you have 3 rotations, rotational degrees of freedom. Okay, and the third one is vibrational. So if I make carbon dioxide, Now we are left with how many? 4 vibrational degrees of the freedom. Okay, so what will happen is that I will represent that by the red color. What will happen is that first will be the both will go in opposite direction to each other. Okay, this will go this side, this will go this side, and then they'll come back. Okay, so either in opposite direction or in opposite direction. So this is called as symmetric stretching. Okay, then we have, sorry, okay, then if you make, what you will have is, you will have asymmetric stretching. But now the issue is, since your degrees of this is moving very high, this is moving low, so in order to counterfeit, this has to move little bit here. Okay, so simply I can represent that by this oxygen will go there, this oxygen will go little bit there, so this will come here. Okay, so this is called as symmetrical stretching. Okay, or this is called as asymmetric. We have a symmetric stretching and we have an asymmetric stretching. So here, since it's a linear molecule, we will not have any bending vibration. So we have two vibrational degrees of the freedom. Okay, so 3 and 2 vibrational degrees of the freedom. Okay, for 3 and minus, just a second, just a second. Okay, so the since we have already shown for, yes, so for a for a linear molecule, the vibrational degrees of freedom are 3 and minus 5. For a linear molecule, just like we have shown here, it is, I will clean this, vibrational degrees of freedom are 3 and minus 5. So here that is 4, there will be 4 types of the vibrations. Okay, and uh, for a non-linear molecule, it will be 3 and minus 6, or 3 vibrational degrees of the freedom. Now we have shown 3 translational degrees of the freedom. We have shown um, there will be 2 rotational degrees of the freedom. Okay, sorry, here it is 2, because here this and this is same, so the r x is actually equivalent to r z. Okay, so this will not be counted. Then we should have a 3 vibrational degrees, 3 uh, uh, okay, now what we have seen here is, we have Yes. Okay, so we have shown two vibrational degrees of the freedom. One is symmetrical stretching, second is asymmetrical stretching. Okay, then we will have two more. That will be if we take carbon dioxide again. Okay, what will happen is that this will go up, this will go up, and this will go down. Okay, and this is called as an in plane bending. Third, then what will be, we will have another, like this is carbon dioxide. Okay, this will be out of plane bending. Okay, so what we have is we have four vibrational degrees of the freedom. Okay, so corresponding to each of these degrees of the freedom, and also we have an electronics. Okay, so corresponding to each of these degrees of the freedom, what will happen is once we give a light or some source of the external energy a particular frequency, a particular mode, it will be a vibrational, electronic, or a translational, it will get excited. Okay, once that excitation will happen, the absorption will happen. Okay, now different energy modes or different vibrations will give us different excitations or different absorptions. Okay, for example, if you take very low microwave. Okay, if you will take for example if we take a microwave. Okay, so what will happen is microwave will excite the rotational degrees of freedom, right? Then if you take little bit higher, for example infrared. Okay, then what it will do is it will excite the vibrational degrees of freedom. That is the reason it's called as um, a rotational vibrational spectroscopy. It also will excite both vibrational as well as rotation. Okay, because each vibrational energy have each rotational has different rotational energies. Okay, this is microwave, this is IR. If you go higher, for example you go UV and visible, it will excite the electronic energy levels. So corresponding to each of the degrees of the freedom, we will have different they will absorb in different frequencies, and as a result they will have different uh, and we'll get different spectroscopies. Now these spectroscopies are depend on absorption. Okay, there can be scattering, like just like the Raman spectroscopy, or there can be nuclear magnetic resonance. No, that is a different story. Okay, that comprises of nuclear states. Okay, so now what the question we have is, let us go back to the question. The question we had is, in a pump probe experiment of sodium iodide by Ahmad Zail and Kogor, the detected emission and oscillation in the emission wire. Okay, we have to see, like sodium iodide we have. Okay, there has been seen emission and there has been seen oscillations in the emission. Okay, so two things we have seen. Where are they coming from? Okay, emission detected was due to Na positive, and the oscillations were due to vibration of Na bond in the excited state. Okay, emission detected was due to Na atoms, and oscillations were due to Na bond in the ground state. Okay, emission detected was due to Na atoms, and oscillations were due to the vibration of Na bond in the excited. So third is actually the answer. How? Because if you see, what is this? This is question 5. I have already written. We have here n I. Okay, so this is Na and this is I. So what will happen is that, okay, what will happen is these things will vibrate. Okay, okay, so these things will vibrate. Because of that vibration, as I have told you, we will determine the vibrations in the vibration in the spectrum. And because of the sodium atoms, since the sodium atoms has weak bound valence electron that can get excited. or and because of that you will see an you will see the emission because of that sodium atom. Because what will happen is Na positive we have, and then once electron is added to the Na positive, what it will become Na. Now it will lead to some of the loss of the energy in the form of E. So this is the emission. So third is the correct answer. Okay. Now we have a sixth. We have sixth. Consider a reaction. Reaction is going to product us. The possible pathway for the reactions are R gives I to, okay, so we have a reaction in which the reaction goes from reactant to the products. Okay, now there are two possible pathways. One is through an intermediate and second is without an intermediate. Okay, so intermediate is there are two different things that we see in a reaction. One is an intermediate and one is a transition state. Transition states are very highly unstable compound. Okay, unstable chemical structures, they cannot be isolated, but intermediates can be isolated under certain conditions. Okay, so if you see for example what we have a question, see this. So for example, if you see a reaction. Okay, so this is my reaction coordinate, this is my, okay, this is my energy, and this is how the reactions are happening. So what actually happens is you have a reactant here, it goes up, then it goes like this. Okay, so sorry, I'll just make it a little better. Okay, okay, for example, we have this. So here we have our reactant A. Okay, here we have a transition state first, here we have a transition state second, here we have an intermediate, and here we have a product. So this reaction it involves the transition. You see that at the top of the energy states, where there is maximum energy from here to here. Okay, so as I discussed it previously, this is called as an activation energy. Okay, this is for the forward reaction, and this activation in energy is for the activation energy for the backward reaction. Okay, and this is the intermediate. Now this intermediate comes in between the two transition states. Okay, since the energy of the intermediate is less than that of the transition states, they can be under certain circumstances they can be isolated. Okay, but the transition states are highly unstable, and they cannot be they can just be approximated. Okay, but they cannot be isolated, or we can see some of the signatures for the transition states but cannot be. So this is the difference between a transition state and a intermediate. Okay, now the reaction here is shown is there is a particular reaction that can happen two ways. One is through the intermediate and second is directly. Okay, now we have been shown that if the reaction proceeds through the intermediate like K1 and K2 through the intermediate I. Okay, now what will happen is that there's a two-step process. Okay, intermediate to, and we have a rate constant K1 and K2. Similarly, we have a rate constant K1 dash if it goes directly. Now we have been told what will be the possible pathway for the reaction. Now from this scene what we have seen is that, and also K, and given that the information that is given is as a rate constant, K1 is greater than K1 dash is greater than K1 plus K2. Okay, so the K1 dash is greater than K1 K12. That means, see, the reaction rate constant, it indirectly tells us how fast a reaction is. Okay, if for example we take two reactants. Okay, this is a reaction intermediate that is going this way. For example, if we take two reactions, one is A getting converted into B, and one is A getting converted into C, and this is K1 and this is K2. Now we know that rate of a reaction, for example, is equivalent to K1 then A for first step for this reaction, but rate of a reaction is equivalent to K2A for this. if K1 is greater than K2. So what will happen, since K1 is greater than T2 and we take initial concentration of both the constant same, like A and A is both constant, so we take two containers where there is A and A, one reaction proceeds to B, second reaction proceeds to C. Now why they will go to two different products will depend upon the environmental conditions. Probably under different environmental conditions you can have different compounds, or you can have different products. Okay, that I have shown that previously, that thermodynamically stable compound or a kinetically stable compound, under certain conditions you can get one product, under other conditions you can have another product. Okay, so the basic chemical engineering is what we do, we want to facilitate a particular product. When you are doing a reaction, okay, you can have side products. Now you don't want those side products, you want a main product. Okay, the basic chemical engineering, in what we do is we optimize that reaction so that it will give us our compound that we want in majority of the quantity, or only that compound, and it will not give any other compound. Okay, so that we have to optimize. It will depend upon the environmental conditions and everything. Okay, so if we see that K1 is good, that means rate of reaction 1 will be greater than rate of the reaction 2. Okay, so from this we came to know that. Now here what our question is, the question is that we have an A that is going to an intermediate, and that is going to a, we have an, sorry, we haven't, sorry, this is okay. The question that we have is, we have an R that is going to intermediate, and that is going to the product. Okay, so this is K1 and this is K2. Now there is another pathway for the same reaction where uh, R is directly going to the product through K dash. Now the information that is given is K dash is greater than K1 is greater than K2. Okay, now you see, when the rate of the reaction is faster, okay, you know that rate of a reaction, for example, we consider simple Arrhenius equation. Okay, simple Arrhenius equation, which determines that rate constant K is pre-exponential minus E. Now you might have seen this equation. Now this is Arrhenius equation. Okay, it correlates the K as a function of EA. Now higher the value of EA, lower will be the K. Okay, and K is that means K is inversely K is proportional to 1 by EA, so inversely proportional to EA. Okay, so this tells us that if we have a higher EA, you will have a lower K. Okay, so for the reaction that we have been given is, if we plot it, we have two steps. One is two-step process. Okay, the second is a second step process. Okay, so both reactants is becoming products. This is our intermediate here. Okay, now for this reaction we are determining K1, this is K2, and for this reaction we are determining K1 dash. Now you see, this is reaction coordinate, for example zeta. Okay, now you see the rate, the product will always go through the lowest activation pathway, it will not go to the highest activation pathway. So all the product that will be formed through reaction pathway second, because the rate of the reaction is the fastest. Okay, so the fastest once it is the fastest, the reaction will go through that part because the activation energy required is less. So the correct option we have is the rate determining pathway will be uh, C, B, A, C. Okay, so that is the correct option. Okay, now let us go to the next question. Okay, now we have question number 1. If the initial concentration, okay, question number 7 we have, if the reaction 2NO plus F2 undergoes the following mechanism. Okay, so we have a reaction in which the 2NO plus F2, it undergoes the following mechanism. Okay, the rate of the reaction is, okay, so this is regarding the rate of the reaction we have to determine from the, this is a complex reaction. Okay, so we had, since individual reactions are given, and we have to determine what is the rate of a reaction, rate of reaction with respect to NO2, because two molecules are reacted. Okay, two NO2 molecules are reacted in one element, in one reaction. Okay, so we have to determine, since the mechanism is given, so from that mechanism we can determine the rate of the reaction. Okay, so we'll simply use the rate law equations to determine uh, the rate of the reactions. Okay, so we have question 7. Okay, so we will write what is the ORR reaction. This is our ORR reaction. Here the ORR reaction is two molecules of NO2 react with F2 to form nitrous fluoride. Okay, so what will be the rate of the reaction? It will be minus, because there is degree, if we minus 1 by 2 d of decrease in the concentration of NO2 as a function of dt. Also the rate of the reaction will be, since F2 is 1, we'll write minus d F2 by dt, which will be equivalent to 1 by 2, since there is product of formation d of NO2 F by dt. Okay, that will give us the rate of the reaction. Okay, okay, now from step 2 of mechanism. Okay, rate will be given by if we take the second step of the mechanism, it will be K2 F NO2. This will be 1. So where I have taken this is because the second step of the reaction that is shown is F plus N2 NO2 so this step. So what will be the rate of this reaction? It will be K2 and then concentration of this multiplied by concentration of this. Okay, that will be the rate of formation of this. So this is now what we have to know is, since we want to know this F. Okay, because F is a sort of an intermediate in this process, it's not generated. Now what we'll do is we'll apply a concept, applying the steady state approximation. Okay, so we will apply the steady state approximation to F. So what does steady state approximation tell us is that intermediate C, if we will write the steady state approximation. Okay, so we have three products here. Okay, we have reactants, so after initial time reactants will go like this. Okay, so this is our R. Now similarly we have products, so products will go like this. Okay, this is products. And then the third class of compounds that we have is intermediates. Intermediate will go like this. This is I. So this is concentration, this is as a function of time. Now we see after some time the concentration of intermediate remains a constant, so this is called as a steady state approximation. Okay, so thus that means a change in concentration of intermediate, which is our F here, as a function of time after some time will be equivalent to 0. So and product will go on increasing, the reactant will go on decreasing, but after an initial lag time, once the intermediate is formed, okay, then it remains constant, because rate of formation of intermediate is equivalent to rate of uh, reaction of the intermediate. Okay, so what we'll do is we'll write dF is our intermediate by dt will be given by K1 NO2 F2 minus, whereas this K1, what it will tell me, it is the rate of formation of F in the first step. Okay, what is the rate of using F or reaction of F? It is the rate of the second reaction. It should be equivalent to 0. Cool. Now what we'll do is we'll do some rearrangement. K1 NO2 F2 should become equivalent to okay. Okay, because here what will happen is that this NO2 and this NO2 will go cancel. So we have determined concentration of the steady state concentration of the F. Okay, now using equation 1 that we have shown here, what is the rate of the reaction? That is given by K2 F NO2. Okay, so we will put the value of F. Now then we will determine the rate is given by K2 here, NO2 is equivalent to K2, this one, multiplied by K1 by K2 F2 NO2. Okay, so rate will be given by minus 1 by 2 d by dt NO2, that is given by K1. What we'll do is this and this will cancel. F2 NO2. Okay, so what we have determined is we have determined the rate of reaction to be equivalent to K1. So what you have to do is you have to put the rate of the reaction in terms of concentration of the reactants initially and the different rate constants. Okay, so if there is an intermediate, we can use the steady state approximation, or also the rate is always equivalent to that of the rate of the slowest step. Okay, so once you use those approximations, then you determine the value of the intermediate, the concentration of the steady state intermediate, and from that you can determine how much is the rate of the reaction. Okay, so that completes our question number 7. Okay, so that completes our question number 7. Okay, now we'll go to question number 8. Okay, in question 1 above, okay, we have to go some question 1. If the initial concentration of NOBr is 4 in 10 to the power, how much will it time to take this molar of, okay, so what this is regarding going back to the question number 1. So what they are saying is that if the concentration of NOBr is this much, how much it will take to NOBr. So we have to determine, we have been given the initial concentration, and we have to determine the concentration of, we have to determine the time that it will take, so that the concentration of the reactant will be equivalent to that of. So we'll see what is question 1. Okay, okay, this is our question 1. The decomposition of NOBr to NO is, and the rate rate constant is given. Okay, and the rate constant is given. So we have NOBr goes to NO plus Br. Now we have okay, so we have question number 8. This is working slow. Okay, so what we have is given, we have been given the rate of rate to be NO. The reaction that we have currently is twice NO plus Br2. Okay, so also NOBr used up will be given by 1.5 into 10 to the power minus 3 molar. Okay, now we have to determine how much is NOPR left. That means we have to determine the concentration A, so that is given by 4 into 10 to the power minus 3, that is our initial concentration, minus the amount that has reacted. Okay, so 1.5 into 10 to the power minus 3. Okay, that gives us 2.5 into 10 to the power minus 3 molar. Okay, now we have a we already know, we have determined it from this, that from the rate constant, that it is a second order reaction. Okay, now for a second order reaction, what we'll have is 1 by A. So A is amount of reactant that has remained unreacted after time t, will be given by 1 by A naught plus 2 k t. Okay, that means 1 by 2.5 into 10 to the power minus 3 is equivalent to 1 by 4 into 10 to the power minus 3 plus 2 multiplied by 0.810 multiplied by t. This k that has been determined from question 1, it is 0.810. Okay, so while solving this equation, what can we say, that is, we'll rearrange it. So what we'll get is 1.620 multiplied by t will be equivalent to 400 minus 250. Okay, so t will be equivalent to 150 divided by 1.620, that will be equivalent to 92.60. so the time that is taken will be 92.60. now what was our initial question? So this is the correct answer, 92.60 seconds. Okay, so we have determined it from the rate constant. So if we know for a particular reaction what is the rate constant of the equation and what is our initial concentration, we can, and what is the order of a reaction, we can determine at any amount of time what will be the amount that is unreacted, what will be the amount that is reacted at that point. Okay, so that is for a for any order of a reaction. Okay, now we'll have question number 9. Okay, for a hypothetical fourth order reaction, the units of the rate constants will be. Okay, so we have to determine for a fourth order reaction what are the units of a reaction. Okay, as I have told you in the previous lecture also, from different order of a reaction, the rate constant will have a different units. Okay, so that will briefly discuss here. So we have question 9. Okay, so our question 9 says unit of fourth order reaction. Okay, so if we say that you know, we have a rate of an equation, it is given by k is our rate constant, A is our concentration, and N is the order of a reaction. The rate has a concentration of mole per liter per second. Okay, we had to determine the value rate constant for K. This has a rate constant of mole per liter. Cool. Raised to the power n. Okay, so what we can do is we can rearrange. K will have mole per liter per second divided by mole raised to the power n. Liter, since it is -1, it will become -1, and there is no s. Cool. So K will have, if we take that arrow, it will be mole, since it is already 1, right, we'll write 1 minus n, where n is the order of a reaction. L minus 1 plus n s minus 1. So K will be equivalent to mole 1 minus n L n so sorry, so since this is here, we have done a little mistake. Yeah, see, so we'll have -1. We have -1, then this n will go up, so it will become plus n. Okay, so we can write here, sorry, n -1 per second. Okay, now this is our for any order of a reaction where n is order of reaction. Okay, so if for a zero order reaction n is equivalent to 0, so that means we are dealing with a zero order reaction. Then n will be equivalent to 0, so the rate constant will be mole per liter per second. Okay, for n equivalent to 1. Okay, that is first order reaction. Units of the K will be, n will be equivalent to 1, 1 minus 1 is equal to, that means mole of 0, this n will be equal to 1 minus 1, it will be per second. Okay, similarly if n is equivalent to 2, okay, that will be our second order reaction. We have K will be given by n is 2, so it will be per mole liter per second. Okay, similarly we have n is equivalent to third order reaction, sorry. for a third order reaction, we will have K is equivalent to third order reaction. Okay, so N will be 3, right? So then we will have mole per scad L square S minus 1. And now we'll come into our interest, that is the fourth order reaction. For a fourth order reaction, K will be given by, okay, we have mole per cube L cube per second, right? So we'll see where is it. Third is our answer. Okay, so what I have determined, I have determined a general I got a general equation. This general equation tell us like how what the rate constants we can determine for any sort of a reaction. So using this equation you can determine the rate constant or rate constant units of any order of the reaction. Okay, now we will have we have a last question, that is the 10th question. For the first order reaction, uh, T75, okay, is the time taken to complete 75% of the reaction. So we have a first order reaction, and in which the question says that T75 is the time taken to complete 75% of the reaction, okay, and T50 is the time taken to complete 50% of the ratio of T75 to the T55 will be, okay. So we have to determine what will be the ratio of time taken for the 75% of the reaction to go to completion, and the time taken to for 50% of the reaction to go to the completion, and the rate of the and the order of the reaction given is first order reaction. Give me 1 minute. Okay, so first what we will do is we will derive the integrated rate law equation for a first order reaction. Okay, so we have question 10. Okay, the question 10 tells us about the first order kinetics. This is going little slow, so I'll just close this app for 1 minute and then start again so that it will work fine. Yeah, so we have the first order kinetics reaction. So for a first order kinetics, we know that rate is given by k a raised to the power 1. So rate of a reaction, if a is giving products, so the rate will be given by, obviously, the decrease in the concentration of a with time, right? That will be given by rate of the reaction. But since it's the first order reaction, we know this. Also, we can write dA minus d divided by, we do a rearrangement, by a will be equivalent to k dt. Okay, so now what we will do is, we will do an we'll integrate this equation. Now we have to see what are the limits. Okay, when t, that means time, is equivalent to 0, what was the concentration of a at that time? A naught, because that is the amount we have taken. When t became equivalent to t, that means a particular time, the concentration of a remains this is the unreacted. Okay, so we will integrate between these two. So what we'll do is minus integration from lower limit is a, higher limit is a naught t a by a is equivalent to k is a constant, integration from lower limit. So at a, how much was our this t to 0? Okay, higher limit is 0 d t. Okay, so what we can rearrange this little bit. This is actually 1 by a dA, right? K dt. So we know this equation, it is minus ln of a, but we have integration units from so what we have used here is, because integration of 1 by x d of x is just equivalent to ln of x. That I have used it. Now we take this equation and we subtract, we'll take minus, so we'll reach here. Okay, minus, we have to take upper limit is a naught, so ln of a naught minus ln of a will be equivalent to k, integration of t is t only, so we have to write 0 minus t. Okay, so this will become ln of a minus ln of a naught is equivalent to minus k t. Okay, so we know that what is ln of this equation, ln of a minus ln of b, it will be given by ln of a by b, right? So same thing we'll do, this will be ln of a by a naught will be given by minus k t. However, what we can do is, we'll take the negative here, ln of a by a naught will be equivalent to k t. Okay, so this we can do is, we can reverse it. Okay, now we'll put the value of k will be given by, if it's k, we'll rearrange this 1 by t ln of a naught by a. This is t, this is k. Okay, since we know that ln is 2.303 log, cool. So we can write, actually this is ln is with respect to e and log is with respect to 10. Okay, so then we can write k is equivalent to 2.303 by t log of a naught by a. This we can cover, cool. So we have determined this equation, that is the integrated rate law for first order reactions. Okay, first order reactions. Now this is the first order reaction. Now what we have to do is we have to see like 50% comparison. Okay, now if we see what our question says, the question says for 75% completion, when the compound, when 75 reaction has completed, that means 75% of a naught has reacted. So amount of a naught remaining after t 75, how much will the amount of k naught remaining? It will be directly 100 minus 75, since it is both percent, into a naught. So that gives us 0.25 a naught. But this is also equivalent to a, this is amount unreacted after some time t. Okay, yes. So this is also equivalent to 25% of this. So that means t 75. Okay, so this equation, okay, will be equivalent to 1 by k, sorry, k 2.303 log of a naught by a is our equation. So this is our equation, right? Now we put the value of it. So t75 will be equivalent to 1 by k multiplied by 2.303 log of a divided by 0.25, sorry, a naught divided by 0.25 a naught, right? So from this equation we can see that this and this is cut. Okay, so t 75 will be equivalent to 2.303 by k log of 1 by 0.25. That means 2.303 by k log of 4. Okay, log of 4. So we can so this is our equation for time that is taken for a first order reaction to go for 75% completion. Now we have a second case, that is for 50% completion. A, how much a will be amount? It will be 0.5% of A naught. Okay, so take the above equation, that means T50 2.303 by K log of A naught by A. So put the value of A naught 2.303 by K log of A naught by, this is 0.5 A naught, right? So this will go, and as a result what we'll get is T5 is equivalent to 2.303 by K log of 1 by 5 is log of 2. Okay, so ratio of T35 by T50, it will be T75 by T50 will be given by 2.303 by K log of 4 divided by 2.303 by K log of 4 2. This and this will go. Okay, so T75 by T50 will be given by log of 4 by log of 2, but we also need log of 4 is 2, sorry, log of 2 raised to power 2 by log of 2. We also know that log of m raised to power n is given by n log of m. Okay, so T75 by T50 will be given by 2 log of 2 by log of 2. Okay, you cancel this one, so it will be equivalent to 2. So what we have is T75 by T50 is given by 2. That means for a first order reaction, the time taken to go to 75% of completion is twice as that of the time taken to go to 50% completion. Okay, so if we go back and we see that 2 is the correct answer. So what we have done today is we have yeah, so what we have done today is we have solved the equations for the first order reaction, and we have solved the equation regarding the chemical kinetics. Okay, so I'll give the briefly overview of what we have done in the previous lecture also. Okay, so okay, the first question that we had solved in the how the rate of the rate, how the order of a reaction can be determined from its rate constant units. Different orders have different units, so from that we can know that what is the order of a reaction. So I have briefly explained what is the order of a reaction. Okay, so then I have explained that how different orders of the reaction can be how the integrated rate law depends on the orders of a reaction, how the rate of the reaction depends upon the concentration of the reactants. Okay, then we have briefly discussed about the chemically kinetically driven product or thermodynamically stable product. Okay, so if you have given enough time for a reaction to proceed, then you will get a thermodynamically stable product. Okay, thermodynamics is determined by the delta G of a reaction. That means the total Gibbs energy change when the reactants are converted into the products. But kinetics is determined by the activation energy. So activation energy is the energy that is the surplus energy that is needed for the reactant to form the transition states. Okay, so the concept of this transition energy, it came from the transition state theory. Okay, so the transition state and there is an intermediate. So intermediate is always in between two transition states. Okay, so intermediate is something that can be isolated under very certain conditions, but the transition state is highly hypothesized hypothesized chemical entity that cannot be separated. Okay, so it can be approximated. Okay, so that is our transition state. And then I have shown that under which conditions we'll get a chemical compound kinetically driven product, and under which conditions we'll get a thermodynamically driven product. Okay, then we had the concept of the consecutive reactions. Now majority of the chemical reactions, they are not elementary reaction. Elementary reaction is a single step reaction in which A and B convert into C in a single step. Okay, for them, for these reactions, the order of a reaction is very simple. It is the number of the molecules that are involved in that particular reaction. That means just like from the collision state, so we can say that A and B, they react to form the C. So if one molecule of A and B combine together to form the C for an elementary reaction, then the rate of the reaction will depend on both A as well as B if both are not if none of them is in abundance. Okay, so there's, if one of them is taken in very high concentration, then obviously the rate of the reaction will not depend on that. Okay, so these methods are actually used to determine the order of a reaction with respect to particular reactant when all other reactants are kept in abundance. Okay, so these are called as an isolation methods that you might have heard in your secondary classes. Okay, so then we have shown that for consecutive reactions, what will happen is that different products are formed, and the rate law and the order of a reaction can be negative, can be fractional, and can be the positive for complex reactions. These complex reactions, they proceed with multiple steps, and from each steps we can have some transition state or we can have some reactants. Now we can use the steady state approximation in order to determine the rate of a order of a reaction or rate of a reaction. Okay, so what the steady state approximation states is that after some time the intermediate remains constant. After so once the reaction is started, first the intermediate concentration will go high. Okay, when the reactants are combined together, then once the products start forming, the intermediate concentration will decrease. Okay, now then a particular time will come after a very short transient time where the formation of the intermediate is equivalent to the reaction of the conversion of the intermediate to that of the product. So as a result, the concentration of the intermediates remains constant. Thus, the change in the concentration of reactants is zero. Now that is called as a steady state approximation. Okay, and also there is another approximation, that is the rate of the reaction is always determined by the slowest step. Okay, so if we have a multi-step reaction, this is not an actual approximation. Oh, okay, so if the rate we have a multi-step reaction like A, B to goes to B, goes to C, and goes to D, then rate of the reaction will always determined by the slowest step. Okay, because all other steps are very fast, the only the stopping point is the slowest step. So we can use these approximations in order to determine the total order of a reaction with respect to reactants and the products. Then we have determined it for a zeroth order kinetics. Okay, since for a zero order kinetics, the rate does not depend upon the initial concentration, how much it is taken. Okay, but it will depend, but how much amount of a reactant will be left after some time, that will depend upon how much initially we have taken it. Okay, okay, then we have I have in a pump probe experiment, then I have shown you that there are in a particular molecule or a particular, and there are different degrees of the freedom. Okay, so these degrees of the freedom, what they will do is, once you give energy to the system, that system will absorb that energy into, and some interest its degrees of the freedom. The degrees of the freedom can be electronic, it can be vibrational, it can be vibrionic, both vibrational and electronic, or it can be rotational vibrational, like rotational energies are excited and the translational energies are excited. Okay, so depending upon the type of the frequency or the type of the energy photons that we are giving, that particular excitation will happen. Now not always all can happen, but it depends upon how much energy we are providing. Okay, so the quantization appears or here, that is the reason we see different colors because of different objects, because some color is observed and complementary color is given. Okay, because there is a quantization. Okay, then we have shown that how a vibration can only happen when you have a vibrational degrees of the freedom. Okay, that's for a diatomic molecule. So for sodium iodide, the vibration will come from that, and when there is an de-excitation from an electron to the sodium and positive atom, it will release some energy, so you will get an emission spectra. Okay, then we have a consecutive reaction, and we have determined that how the rate of the reaction or the rate constant depends upon the activation energy. We just use the simple Arrhenius equation, in which it is inversely proportional. The higher the activation energy, lower will be the Now there are other factors like pre-exponential factor and the temperature at which we are doing. Now, we are not considering that, so keeping others constant, we can see that a particular reaction can have different products. Okay, so depending on the environmental conditions, it will depend upon what the products we are getting. So once so we can optimize a particular reaction in order to give us a different product. That's what the industrial people do. Okay, so we have shown that the rate constant, which is the highest, only that reaction will proceed at if a product, if a reactant can form a product into different pathways, the only that pathway is formed which has the highest rate constant or the lowest reaction rate or the lowest activation energy, because only a small amount of the activation energy is required for the reactant to form that product. Now it is not completely uh, possible that only through that reaction the product will form. There will be some of the molecules of the reactants, if available at that particular temperature, that will have enough energy to go to the higher activation energy pathway. Now that's also possible, and it will depend upon the temperature. Now that if you see use the common kinetic theory of the gases, we can determine that how much fraction of the molecules have enough energy to go to the reactant. That means how much enough of the molecules have activation energy to form the products. Now that is where the collision theory of the kinetics comes. It considers the kinetic theory of the gases, and from that we can know how many collision frequency is, how much activation energy is there, Maxwell's Boltzmann distribution, and we can determine that how much the products and how many percentage of the molecules have which have enough energy to cross the barrier and thus to form the product. Okay, then we have determined that what is be the rate of a reaction using the state approximation that I have already explained, and then we have been given the initial concentration of this, and we have determined the, so from the integrated rate law we can determine what will be the concentration of the reactants left or the products formed at particular time after the state of a reaction, provided we know the reaction rate and the initial constant for any order of the reaction. Then we have the order of the reaction is four. Usually we don't have the four order reactions, but hypothetically if we have the order of a reaction 4, what will be this rate constant? Now I have already told you how we can determine it from the uh, uh, units of the rate constant. Okay, then we have the first order reaction, how much time it will take to form 75% and how much time it will take to form the to get 50% completion, and we had determined that it is the double the time is taken for a first order reaction to go to 75 completion to that of the 50% completion. Now this completes our today's talk. I will see you in the next one. So all these lectures and the notes will be available on the NPTEL link. Okay, thank you so much.